Hello dear students, welcome back once again. I guess we have discussed enough about alcohols in phenol, so today let us discuss a little about these ethers. Now ethers are organic compounds that have the general formula ROR dash. Now these two R's may be the same or they may be different. Both may be alkyl groups. For example, we have two methyl groups here, or it may be different alkyl groups also like this, or both of these R's may be aryl groups also. For example, here both are phenyl groups, and then one may be alkyl group, the other may be an aryl group also. All of these come under ethers. So alkyls have the general formula ROR dash, where R and R dash may be the same or different alkyl or aryl groups. Now, the classification of these ethers is also very simple. They are classified into two types. If both alkyl groups, if both the R's are same, then they are called as symmetrical or simple ethers. Symmetrical or simple ethers. And if the two R's are different, then they are called as unsymmetrical or complex ethers. So we have only two types of ethers. The first one is symmetrical or simple ethers, where the two R's are the same alkyl or aryl groups. So these two, they come under symmetrical or simple ethers. But if the two R's are different, like here, we have methyl group here, we have ethyl group here, we have methyl, and here we have the phenyl group. So these two come under unsymmetrical or complex ethers. Now, the naming is also very simple for these ethers. In the common nomenclature, in the common system of naming, first we name the two alkyl groups in alphabetical order. Then that is followed by the word ether. Suppose we take this example, CH3 OCH3. We have two methyl groups. So the same alkyl group, therefore in this case we use the prefix dimethyl ether. If we have another one, CH3OC2H5. Now here we have two different alkyl groups. These two will be named first in alphabetical order. Now this is the methyl group. The name starts with M. Ethyl group starts with E. So in alphabetical order, this comes first. So this will be named as ethyl methyl ether. This can be named as diphenyl ether. And this will be named as methyl phenyl ether. So in the command system, we just name the two alkyls first, and these names are followed by the word ether in each case. Now if we use the UBIC nomenclature, these are named as alkoxy derivatives of the parent hydrocarbon. So in common nomenclature, this one, dimethyl ether, will be named as methoxymethane. Now in this case, both the alkyl groups are the same. So the O group can go to any one of them. Methoxymethane will be obtained in each case. But if we have two different alkyl groups like this, then the O group goes to the smaller alkyl group. So this will be named as methoxy ethane. Likewise, this will be named as methoxybenzene. So once again, in IUPAC nomenclature, the ethers, they are named as alkoxy derivatives of the parent hydrocarbon. And if there are different R groups, different alkyl groups, the O group goes to the alkyl group which is smaller. Now let us see some methods of preparations of these ethers also. The first method for preparation of ethers is by dehydration of alcohols. Dehydration of alcohols. Now, alcohols, when they are treated with protic acids like sulfuric acid or phosphoric acid, then this gives rise to ethers. Now remember, when alcohols are dehydrated in the presence of these protic acids, we have seen that alkenes can also be formed. We have seen the mechanism also. So to obtain ethers, the temperature should be lower. This should be maintained at around 413 Kelvin. So at this temperature, if the alcohols are treated with sulfuric acid or phosphoric acid, some protic acid, then we get ethers. Now if the temperature is elevated at around 443 Kelvin, then this alcohol on dehydration will give an alkene. So suppose instead of using this general formula, we have C2H5OH. If we have ethanol, if this is treated with sulfuric acid at 413 Kelvin, we get an ether. This is diethyl ether, C2H5O, C2H5. So an ether will be obtained at this 413 Kelvin. But if the same reaction is carried out at this higher temperature, 443 Kelvin, then in place of an ether, we will get an alkene. The mechanism for this production of alkenes from alcohols we have seen in the last class. So the thing here is to maintain the temperature at lower temperatures in order to obtain these ethers. If it is elevated to higher temperatures, then the product obtained will be an alkene. The second method that we can use for preparation of these ethers is the Williamsons synthesis method. Now, in this method, a sodium alkoxide, an alkoxide of sodium, it is treated with an alkyl halide. In this reaction, the halogen atom of the alkyl halide will be replaced by the alkoxide group. So this alkoxide group. So we get an ether. Suppose we have sodium methoxide. We treat it with chloromethane, an alkyl halide. Then this Cl will be replaced by the alkoxide group here. Then we get CH3OCH3. This is dimethyl ether or methoxymethane. So by treating sodium ethoxydes or sodium alkoxides with alkyl halides, we obtain ethers under this Williamsons method. Now, one thing to remember is that the products obtained will be more favorable to obtain ether when we use primary alkyl halides. If we use secondary or tertiary alkyl halides, then usually elimination competes with this substitution reaction. So either an ether or an alkane or a mixture of ether and alkanes may be formed if we use secondary and tertiary alkyl halides. If we use tertiary alkyl halides, we will obtain only alkenes. Instead of ethers, we will obtain only alkenes, and therefore this method is suitable for production of ethers from primary alkyl halides mostly. Secondary and tertiary alkyl halides are rarely used. So those are the methods that we can use for preparation of these ethers. Now let us see some of the physical properties of ethers. The first physical property is that the CO bonds in these ethers are polar in nature, and thus they have a net dipole moment. Suppose we have CH3 OCH3 dimethyl ether. These CO bonds, they are polar in nature because oxygen is more electronegative than the carbon atoms. So due to difference in electronegativities, polarity is developed. And it is due to this that the ethers have net dipole moments. The second physical property is that their boiling points are comparable to those of alkanes of comparable molecular masses, but much lower than the boiling points of alcohols. Alcohols, they have very high boiling points because of hydrogen bonding. Hydrogen bonding within the molecules of these ethers is not possible. So since they lack hydrogen bonding, they will have lower boiling points than the alcohols. But their boiling points are very much comparable to those of hydrocarbons of comparable molecular mass. The third point is that, like in alcohols, oxygen of ether can also form hydrogen bonds with water. So their miscibility resembles those of alcohols. Alcohols are soluble in water or are miscible with water because they are able to form hydrogen bonding with water molecules. That is what we have seen in the previous classes. Like that, these ether molecules are able to form hydrogen bonding with water molecules, and therefore their miscibility with water or their solubility in water is similar to that of the alcohols. So these are the physical properties of ethers. Let us see some of their chemical reactions also. The first reactions involve the cleavage of CO bond in ethers. This reaction takes place under drastic conditions with excess of hydrogen halides. Now, whenever an ether is treated with a hydrogen halide, it can be either HCl, it can be HBr or HF, any one of these can be used. When the ethers are treated with excess of hydrogen halides, then we obtain alkyl halides and alcohols. And these alcohols can also further react with alkyl halides to produce another molecule of alkyl halides. Now, there is a very important point to remember regarding these reactions. In case of mixed ethers having primary or secondary alkyl groups, a haloalkane having smaller alkyl group is formed. However, in the case of ether containing a tertiary alkyl group, the halide formed is tertiary halide. So let us try to understand it with these examples. if we have primary or secondary alkyl groups attached to this ether group, suppose CH3O C2H5, both of these are primary alkyls. In the next one, we have CH3O, then CH, CH3, and CH3. This is primary, but this is secondary. So in this one, we have a secondary alkyl group attached to the ether group. This is also treated with a hydrogen halide. Then in the next one, we have a tertiary alkyl group attached to the ether group here. CH3 group will be primary, but this group is tertiary. Now, in the case of alkyl groups being primary or secondary, the halide form, the alkyl halide form will be formed from the smaller alkyl group. So here, CH3, the smaller group will form the alkyl halide. So we get iodomethane. Then this one will form the alcohol. In the case of secondary alkyl groups also, the halide form will be primary. So we will get CH3I plus CH, CH3, then CH3, and then OH. The alcohol form will be secondary. But in the case where there are tertiary alkyl groups, the alkyl halide form will be formed from the tertiary group. So in this case, CH3, CH3, and then here CH3, OH group will be formed with this group. So we get a tertiary alcohol here and a primary halide, primary alkyl halide. So once again, if we have only primary and secondary alkyl groups attached to the ether group, then the alcohols formed, the alkyl halides form will be primary. That means the smaller groups will form the alkyl halide. But in the case of tertiary alkyl group present on the molecule, the alkyl group will be formed. The alkyl group will be formed with the tertiary group. So I group will come here, and this should be OH, methanol. So in this case, the alkyl halide is tertiary. In the other two cases, the alkyl halide form will be primary. The second type of reaction is the electrophilic substitution reactions. Now remember, in these ethers, if we have an aryl ring like this, these are called as alkyl aryl ethers. Now this alkoxy group, it is ortho in para directing. So whenever substitution takes place, whenever electrophilic substitution takes place, this alkoxy group will direct the incoming electrophile to ortho and para positions. So if this is treated with a halogen like bromine, then this group, the alkoxy group, will direct the halogen, the electrophile, to either ortho or para positions. So we will get two types of product here. One at ortho position and the other at para position. This happens whenever electrophilic substitution takes place in these ethers. That is all for today. Thank you for your listening.